Hi, welcome back. In this lecture, I want to flesh out a few more of the particulars about the concept of path dependence. I want to relate it to our earlier notion of a Markov process, which wasn't in any way path dependent. Remember, we got a unique equilibrium in that case. And I also want to relate it to chaos. And then finally, what I'd like to do is just flesh out a little bit more about why the distinction between path dependence and fat dependence is so important outside of the context of the earn models. I want to talk about it sort of in a real world setting as opposed to within the context of that simple earn model. Okay, so let's get started. Remember, when we talk about path dependence, what we're talking about is the sequence of previous events influencing not only outcome in this period, but possibly the long-run equilibrium. So our definition of path dependence is that the outcome probabilities depend on the sequences of past outcomes. So in the case of a path-dependent outcome, we're just saying the probability of an outcome depends on it. In the case of path-dependent equilibrium, we're saying that the long-run equilibrium depends on the past outcomes. Now remember we studied Markov processes though in a previous lecture. And in the Markov processes, we always got a unique equilibrium. And in a Markov process, we made the following assumptions. We said there's a finite set of states. We said there's fixed transition probabilities within those states that you could get from any one state to any other, and that it wasn't a simple cycle. So it didn't go A, B, C, A, B, C, A, B, C. And then given those assumptions, we got something called the Markov convergence theorem that said that given A1 to A4, a Markov process converges to an equilibrium that's unique. Now remember that was a stochastic equilibrium, so it was moving between the states. It was still churning, but it was a unique equilibrium. So why aren't Markov processes path dependent? Well, here's why. This assumption right here, fixed transition probabilities. Remember in our earn model, we've got this earn, and as we've got red and blue balls in here, and as we pick more red balls, we start adding more red balls. So the transition probabilities change. So it's those fixed transition probabilities that are really underpinning why the Markov process goes to a unique, even though it's a stochastic equilibrium, goes to stochastic equilibrium because we're not changing the probabilities. The history of events doesn't change the probabilities. So now by comparing these two models, we see sort of when does history matter? History matters when it changes the transition probabilities. We have two ways of seeing the effects of history on outcomes. One, through the Markov process by saying history doesn't matter if the probabilities don't change. And then the other is through the earn models by showing history does matter if the outcomes change, if the probabilities change. What I want to do next is relate this to chaos. Now to relate to chaos, I've got to begin by describing something called a recursive function. So a recursive function was sort of implicit in our Markov model and in our earn model, but let me make it more formal. So in a recursive function, what you got is you get an outcome at time t, and there's an outcome function, f, that maps x into itself. So there's this process that's just sort of moving on and on and on. So you basically got an outcome, you get another outcome, and another outcome, and another outcome. So one thing could just be x plus 2. So this would just go 1, 3, 5, 7, 9, 11. So in the earn models that we had a recursive function where we picked out x could be either blue or red, and we picked out blue, red, blue, red, blue, red. But what we got in each period depended on what we picked previously, and in some cases on the whole set. So in some cases, what you get in next period can only depend on a previous variable, or it could depend on what happened in period 1, what happened in period 2, and what happened in period 3. So you could have that x4 is a function of period 1, 2, and 3. That would be a path-dependent process. In a simple recursive function, what happens in this period, f of xt might only depend on, or f of xt plus 1 might only depend on xt. So what happens in this period only depends on the previous period. We can use these recursive functions to describe processes that are chaotic. So when we talk about chaos, what we mean is extreme sensitivity to initial conditions. So what that means is if I start with 2 points that are very, very close to one another, and then I keep applying this recursive function, that what I'm going to get is these paths are going to go in very different ways. So 2 points that start near each other end up a long way away. So let's see an example of that. This is called the tent map. So let x be in the interval 0, 1, and these round brackets mean that I don't include 0, I don't include 1. Now the function is defined as follows. F of x equals 2x if x is less than a half. So here's 0, here's 1, here's a half. So it's just equal to 2x if it's less than a half. And then it's 2 minus 2x if x is bigger than a half. So what that means is that at x equals a half, I'm going to get 2 minus, at x equals a half here, I'm going to get 1. And at x equals a half here, I'm going to get 2 minus 1, which is also 1. So this looks like this, and it looks like a tent, hence the tent map. So the way this works is if I start out at 0.21 and I apply it, I'm going to get 0.42. Well, then if I get to 0.42 and I apply it, I'm going to get 0.84. Well, then if I look at 0.84 and I apply it, then I'm going to apply this, and I'm going to get 2 minus 2 times 0.84, which is going to be 2 minus 1.68, which is going to be 0.32. So I'm going to go back over here to 0.32, and I'm going to get 0.64. So that's how the tent map works. I just recursively go through the function. Here's an example of the tent map where I start with 2 points that are very similar to each other. One is 0.4321, the other is 0.4322. Well, again, first I double it, then I apply 2 minus 2x, then I double x, that's less than a half, then I apply 2 minus 2x, and so on. And notice after I do it just a few periods, these 2 points are now a long way away from each other. So the tent map ends up being chaotic because there's extreme sensitivity to initial condition. Just by being a tiny bit different on the 4th decimal point, you end up a long way away just after 11 iterations of the function. Now I can see this graphically as follows. Originally you can't even see the blue line because it's hidden behind the red line. So this is the same things I just put in, but then over time these two paths end up being very different. This is extreme sensitivity to initial condition. Notice this is not path dependence. Why is this not path dependence? Well, let's go back. This tent map is just a fixed recursive function. Once I choose my initial point, once I choose 0.4321 or 0.4322, then I know exactly what's going to happen. So this is extremely sensitive to initial conditions, but it's not path dependent, because all that matters is the initial point. Now, if you define the path as being the initial point, then yes, it's path dependent. But nothing that happens along the way has really any effect on what's going to happen in the long run, because we know what's going to happen. It's once we choose the initial point, we've just got a fixed function. So chaos, in its standard form, means extreme sensitivity to initial conditions. So the initial point matters, and if I apply this function over and over, tiny differences in the initial point will vary by a lot later on. Path dependence means what happens along the way influences the outcome. So it's typically not a deterministic process, because what happens along the way has an impact on the outcome. So let's step way back for a second. You can think of a process as being independent if outcomes don't in any way depend on the past history of outcomes. We can think of a process as depending on the initial conditions if the outcome or state in a later period depends only on the initial state. It's completely deterministic. So this independence is a probabilistic concept that there's a 50% chance of getting a red or blue ball each period. With chaos, extreme sensitivity to initial conditions, we're saying it's deterministic. We know what's going to happen once we give the initial point, and all that matters is that initial point. Path dependence means that the outcome probabilities, what happens in the long run, depends on what happens along the way. And finally, we have then path dependence, means that outcome probabilities don't depend on the order in which things happen. It only depends on the set of things. So in our Poyer-Earn process, what happens if we've got 24 red balls and 6 blue balls sitting in this urn, it doesn't matter what order they appeared in. All that matters is the number that there are. So that's the difference between path dependence and path dependence. Now, when historians or institutional scholars think about path dependence, they often think in terms of the sequence of events mattering, not just the set of things mattering. They also think that things aren't independent, and they think that although initial conditions matter, they're not the only thing that matters. So they don't think it's the case that once we write the Constitution that what then plays out is completely deterministic. So they tend to side with things being path dependent. Why? Why do they think path dependence and nothing else? Well, independent would mean there's no structure to history, so that doesn't make any sense. Extreme sensitivity to initial conditions and then deterministic processes doesn't make any sense either, because it would mean that fate is just completely predetermined by a few initial choices. So it really comes down to path versus fat. Path says the sequence matters, fat says the set matters. Why do they think it's the path, not the set? That's, I think, seemingly a deep question. And these nice Earn models have helped us make us think about, well, one reason could be that they think this is true, is they think that early events have larger importance. Well, let's think about some events. So let's suppose that this was what American history looked like. That in 1814 we gave women the right to vote. And then in 1823 we had a civil war to get rid of slavery. In 1880 we finished the Transcontinental Railroad across the United States. In 1894 we find gold in California. In 1923 we decide to buy the Midwest from France. So previously, when we put this Transcontinental Railroad through, we had to negotiate with France to put it through what later became the Louisiana Purchase. And then in 1967 we have a brutal war with England for independence. It's hard to imagine that if this were the sequence of events, that I'd be sitting here giving this course to you right now. That it's probably the case that American society would look extremely different than it does now. In particular, I might be speaking French because I would be in what was the former Louisiana Purchase, and we'd probably look a lot more like Quebec here in the in Michigan than we look than I look now. Okay, so when we think about these ideas, path dependence, fact dependence, independence, sensitivity to initial condition, or chaos, what we see is these simple models help us organize our thinking about what the world might look like. And we understand why a lot of historians focus so much on path dependence, because it seems the most reasonable. We also see why people who study gambling in casinos consider independence. And we see why a lot of physicists are interested in things like chaos, because there are actual physical recursive functions that produce this extreme sensitivity to initial conditions. So these simple models help us make sense of a lot of concepts that are actually fairly closely related logically. And the EARN model in particular helps us draw bright lines between path dependence, fact dependence, and independence. Okay, thank you very much.